So, this is a quick introduction to the fundamental theorem of calculus, part one. And what we're going to try to do is connect the idea of the area under the curve to all of the anti differentiation strategies that we've been working on. So, we have here a line that represents the direct proportion between y is equal to mx, and m can represent any particular slope that's on here. So, we are going to use a point down here of 0, comma 0. And also another point on this function, we can call this point x value of b, and then the y value would be m times that b value, depending on what m is going to be. So using the idea of geometry and finding the area under the curve, we have a triangle here where we have 1/2. The base of our triangle is worth b, and the height of our triangle is worth m times b. So overall, the area would be 1/2 m times b squared. Now, when we look at the calculus notation behind this, using those definite integrals that we looked at before, this would start at 0 and go to x equals b, and our function is m times x. So what we're going to try to do is relate what does the area under the curve have to do with the definite integral, and how are they connected to each other. So we're going to start plugging in some numbers and taking a look at what happens when we have actual values for our slope. So if m was equal to 1, for example, our function would look like just 1x, and the area would be 1/2 times our m value of 1 times b squared, or 1/2 b squared. And what we're going to do is we're going to repeat that process to find out what would be the area expression for each one of these slopes. So take a moment and figure that out. So here are the resulting areas that we come up with depending upon how big the slope is. The next thing we're going to do in this last column is compare what would happen if we took the antiderivative of what is inside the integral. So working with the very first integral for m is equal to 1, we have x as our integrand. So the antiderivative for x would be 1/2 x squared plus c. If we had 2x as our integrand, its antiderivative would be x squared plus c. For 5x, we'd be looking at 5/2 x squared plus c. And then for negative 7x, we'd be looking at negative 7/2 x squared plus c. So what we want to observe is what kind of connections can we make between our antiderivative and the area of our triangle. So take a moment to look at each one of these with the antiderivative and the area of the triangle and see if you notice any patterns. One of the things that you may notice is that um, uh, the area value we have is almost identical to the antiderivative if we were to replace x with the letter b. So if we were just to plug b into our antiderivative and assume c would be 0, then we would end up with the same expression as our area. Another way to look at this is to compare our general form, so the integral from 0 to b of mx dx, which we know that if our slope is m, we're going to end up with 1/2 mb squared as a total area, and compare that to what would happen if we just did the general antiderivative of mx dx. The two expressions are identical, aside from that plus c. Only with our area, we have the b plugged in for that value of x. So what does this mean for us? If we need to find an area under the curve, we can start off by taking the antiderivative of our integrand, and then we can plug in that upper limit of integration that we have up there in for our value for x. So the next question would be to ask, does the plus c have anything to do with this? What happens if we don't have a 0 in the denominator? So we're going to take a look at another example, this time moving away from triangles and moving into trapezoids to see if we can figure out what happens to that plus c and what happens to that 0 in the bottom. So here's our trapezoid. Using geometry, we're going to have an area that'll be 1/2 our height times base 1 plus base 2. That's the generic formula for the area of a trapezoid. Now in this case, our height is designated by the difference in our x values. So from b minus a, that kind of represents the height of our trapezoid. The base 1 and base 2 values come from the y coordinates at the ends of our trapezoid. So this point right here is a comma m times a. This point up here is b comma m times b. So our base 1 and base 2 values will be m times a and m times b. Now we're going to use a little bit of algebra here just to kind of make this a little bit more simple. I'm going to factor out the m out with that 1/2. So we get 1/2 m, we get b minus a, and a plus b. Hopefully you're noticing that those factors actually make a difference of perfect squares. So we've got 1/2 m times your a b squared minus a squared. This is also the same thing if we distribute this again, 1/2 m times b squared minus 1/2 m times a squared. If you consider this last expression right here about what this means about triangles, the 1/2 mb squared would be the triangle that's the larger triangle represented in this situation. And then the 1/2 m times a squared is the smaller of the two triangles. What we're doing is we're taking the larger triangle area and subtracting out that empty triangle space of the smaller one. Now let's compare this to the calculus notation. We are looking at the area under the curve from a to b of our function m times x dx. So we know that this area under the curve can be represented by 1/2 m times b squared minus 1/2 m times a squared. So again, what we want to notice is what kind of pattern are we falling into using the general antiderivative. So let's write down kind of the three situations we have here. We have the integral from 0 to b of mx dx that we figured out that's the area of the triangle, which is 1/2 m times b squared. We now just figured out that from a to b, where a is not 0, we have the area under the curve of mx is 1/2 mb squared minus 1/2 ma squared. And we also have the general antiderivative without any kind of bounds on there would be our m over 2 x squared plus a c. So look at the comparison of all these. If this is our general antiderivative of just m times x, when we go from 0 to b, we come up with this area that just plugs in the value of b. And when we go from a to b, we're just going to be plugging in the value of b and also the value of a, but subtracting them. The general antiderivative can help you determine what the exact area under the curve is going to be between any two x values. So when we're given an x value of a, and an x value of b, we can use our general antiderivative to determine what the exact area under the curve is going to be.